Okay. So from my experience, good keynote talks are short, and they come primarily from people who are working directly in the topic. Industry talks are usually better than academic talks. I'm a little bit sorry that I'm an academic and not an industry person, but I'll try to make this talk short, concise, and more full of ideas instead of full of equations, because I also noticed that those are better keynote talks. And as Ollie mentioned, I'm going to try to make the talk focus on two things. The ideas that I've been working on recently and things I think anybody here could take on as new directions. But also, at the end, I'm going to discuss some work on what I think the field is, where I think the field is heading to, and sort of open up for discussion. I hope that there's fruitful discussion after my talk in the Q&A. Before I start, though, let me just point out what IoT is. IoT, for those of you who don't know, it's the Internet of Things. And it's going to become evident as I go through the slides. I want to talk about why we're doing NILM, and should we be doing NILM now that we have everything connected to the Internet. And so that's sort of the motivation behind the slides and what I'm going to be using as the umbrella topic for everything I'm going to be covering. Obligatory slide just to acknowledge the help from a lot of people that I've been collaborating with over the past few years on all the projects that you're going to be seeing here. This is a picture from when I had hair and when I had a lot of beard. These are some of my students from back then. I have a lot more, but I don't have pictures. And I have collaborators all over the world, more than I can fit here, but just to have that obligatory acknowledgement slide. Okay, so here's the outline. I'm going to be talking about, first, some definitions and context so that everybody's on the same page. Ollie already did some of that. I'll add a little bit of thoughts on that, just 10 minutes on that. Then I'm going to spend most of the talk talking about opportunities. I want this talk to be optimistic, so I'm going to show you some of the things where I think opportunities exist, a few million-dollar ideas that I hope that somebody goes on and starts making money out of it. Then jump into challenges. So these are million-dollar ideas, but these are million-dollar ideas that would drain you $1 million. So challenges, things that I think we should avoid. And then, is there a future for NILM? This, even though it's a question, I'm not intending to really answer it. I'm more intending it as a segue for discussion at the end. I have my personal opinions. I'm going to show them here. But I'd really like to hear your input on this because I think it's something that we all, not anybody in the room knows for sure. And then obviously I'll leave some room for questions and answers. Okay, so definitions. The first definition we need to come to an agreement on is what is NILM. And this is a slide that I've been using on a lot of the previous times I've talked to communities like this. And I think everybody agrees on this. So NILM is basically a tool or a set of tools for estimating the energy consumption of individual appliances. Typically, you do this from measurements of voltage or current, or a combination of both, and you take those measurements at limited number of locations throughout the distribution system in the building. So I guess, does anybody do NILM in a way that does not conform to this? That's probably a good question. Okay, so this is a fairly broad definition of what NILM is. Within that definition, though, there's a ton of different ways in which you can solve the problem. So here's a different version of what Ollie presented about the popularity of this topic. And what I did is I took this set of keywords into Google Scholar and took the results from a few different decades. So by decade, I had 3 articles between 1980 and 1990. And can anybody guess what the next few decades, the number of articles are, if you look at this set of keywords? Does it grow linearly, exponentially? Does it not grow at all? Does it stay static? Exponentially. Okay. Just to be clear, when you do a Google image search with those same keywords, it does come up with the things that we care about. And here's the result. So exponential growth, right? And that's kind of what the slide that Ollie was showing also shows. But I wanted to do a control study, so I did the same thing using pachyderm, completely unrelated, or at least in my mind, completely unrelated, just to make sure that that also doesn't grow exponentially. It's not a function of the fact that everybody's publishing more. So here's the image search for that, and this is the linear growth, right? So at least compared to pachyderm, this is growing exponentially. So why is it that we are growing exponentially? I guess there's a couple of reasons, but I think one of the main drivers for this is the fact that now we have a lot more data to work with, whereas before 2000, we didn't have a lot of data to work with. So there's a lot more business interest in actually doing this because now we have access to all this smart meter data that could actually be used. Okay. So how do we approach NILM? This is still in the context phase. So there are a couple of ways. So let's say you have a coffee machine and you want to disaggregate the coffee machine into individual components just to make the problem a little bit easier. You want to recognize when tea is being dispensed, when coffee is being dispensed, and when mocha is being dispensed, and you want to separate all three of them. So there are two approaches mainly for doing NILM. One of the approaches is event-based, where you typically say, okay, I'm interested in looking at the statistically significant changes in the signal and then trying to label those statistically significant changes and identify what they are and then keep track of the individual devices. Typically, this is a supervised setting, so you need to know what these things are and you need to train algorithms to recognize those individual state transitions. And this is a typical pipeline for an event-based system. You start with the monitoring stage, where you monitor an aggregate signal, you detect events, you extract features from it, you do classification, and then you estimate energy. One thing to note here, though, is that this is a feed-forward pipeline, which means that you start with the input here, and you end with something, but there's very little feedback from the end result or from any of the modules back into the beginning ones. So errors accumulate very easily here. So just to pictorially show that, here's the event detection stage. You find a mapping from the signal that you wanted into timestamps that indicate statistically significant changes. Then you extract some features out of those timestamps, which is another function that maps from this into a vector or a set of vectors. And then from there, you train an algorithm that does classification. So basically, you have the pairs of features and labels, and you find a function that maps from the features to the labels, and then in the end you have now the timestamps with the labels associated with them. There's a little bit more than meets the eye here. Obviously, just having classification is not enough. We are interested in getting energy estimates, so going from this time series into the energy estimates is non-trivial. I'm going to talk a little bit more about that in the end, but this is generally what these approaches are doing. In the eventless world, which is the other side of the coin, we do not care so much about the specific change points. We only care about the total decomposition of the aggregate signal. And so these approaches are primarily unsupervised. There are some supervised versions, and even the ones that are completely unsupervised have a little bit of supervised portion on it, if you look at it closely. And typically they can be either probabilistic, they can be based on a blind source separation, which may or may not be probabilistic, or more recently there's also been some work on time series motif mining. Many of you have been working on many of these things, so I'm not going to talk about the details. Just to give you one example, here's the most common way of approaching this problem. You think of each one of the devices as a hidden Markov model. So each one of your devices has a hidden state, which is what operational state it is in, and it emits some observation that you can actually see, let's say power, and then you model that hidden state transition with this hidden Markov model, and you solve the inference problem. It's easier said than done, because this is only one appliance. You typically have more than one appliance in a circuit, and so you need to figure out how to solve that problem, either factorially or individually. There are many different ways of solving it. Okay. So I guess that's what I wanted to cover about context. The question to ask is whether any of your approaches falls outside of any of these two or a combination of these two, eventless and event-based. Okay. So I'm going to count bingo at the end if everything is correct. Okay. So here's the thing, though. All we're doing is using NILM as a tool, because that's what it is, to come up with the disaggregated output, which is what we care about. But how long until this tool becomes obsolete, right? So how long until we are able to get the information we want without having to use the screwdriver that we've been using? That, I think, is going to start to change. And this is, again, the academic view, 10, 20 years down the road. with the advent of the Internet of Things. So why so? Let me give you a simple example. This is a building in Carnegie Mellon's campus. It is perhaps not a very representative building of all the buildings in the US or the world, but it gives you a sense of what we should expect. This is a very regular building, 40,000 square feet, 140 rooms, so on and so forth. In the sense of space and everything else, it's pretty common. But if you look inside, it has a whole bunch of sensing and control points that are accessible to anybody who has access to the building and is interested in getting that information. So panel meters on every panel that sub-meter every one of the circuits. HVAC controllers, thermostats that are digital, fan control units, lighting controllers, so on and so forth. A lot of different sensing points. If you add them all, it's about 5,000 data streams that you can query every second if you wanted to. So the availability of all that data that tells you a lot about how the building is behaving is an interesting opportunity for us to make the same inferences that were interested in originally, which is what are these appliances doing over time. And that's not just limited to commercial buildings. It's also becoming more popular in homes. So if you think about a very expensive home of today, it may have all of these devices in it, right? And that's going to become the wave of the next few years, where we're going to have a lot of our devices communicating exactly what they're doing, or telling us information about the things inside our house without it being the prime objective. So Amazon's Echo, for example, is recording audio from the house all the time. You could probably, from that same stream, tell a couple of different appliances when they're operational and they're emitting sound. Right? So is this the future? Is it possible then to combine the smart meter data that we've been looking at with information from this Internet of Things through APIs, for example, and then come up with a disaggregation output that we wanted to? Or is this the future, where we don't really need the smart meter anymore? Right? That's a question I think is important for us to consider and to keep in mind as we, as the field progresses into the future and we do more workshops like this. So I'd like to point out the opportunities and the challenges in both of those simulated scenarios. Okay, so I think there is hope. Here are 4 of my $1 million ideas. Please give me a share of it if you actually come up with a commercialization of any of them. I'm going to start with side channel assisted NILM, which is generally very related to what we were talking about just now. Then hybrid NILM frameworks that combine eventless and event-based. A little bit about crowdsourced high-resolution libraries. And then lastly, just a few words on unsupervised feature engineering, which I think is an important topic for this field. Okay, so specifically light, sound, electromagnetic field, and APIs. And I'm going to focus more on light and EMF than anything else, because that's where I've done most of the work. Okay. How many of you have looked at information coming from electromagnetic radiation out of an appliance? Okay, you have. It's quite interesting. So we, 5 years ago, created one device that was able to measure electric field and the magnetic field. We placed it around a couple of appliances. It has a 5 to 10 centimeter range. This is in collaboration with Anthony Rowe from Electrical and Computer Engineering. He created the hardware, I analyzed the data, and we basically wanted to use this as a way to get ground truth data for our NILM experiments. But also, we were just interested in knowing what else our appliance is emitting outside of just the power that we were measuring. So let me give you a brief overview of how this works. You can place this sensor close to any wiring in your house, and because it does both electric field sensing and magnetic field sensing, you can detect various different things. So let's say that you have it next to a switch, actually close to the wire that's coming out of the switch in the wall. And that switch is connected to a ceiling fan. So you turn on the switch, and that's event A here, or here if you're looking at here. And when you turn on the switch, there's actually voltage, there's a voltage potential on the line, so the electric field changes, and this thing is reflecting that. You can see that. Even though the fan is not spinning because there's no current flowing, the electric field tells you, I'm located in the right place. You are next to a wire, a live wire. And then when you pull this cord, and the fan starts to flow, then current starts flowing, and if you look at the RMS of this magnetic field signal, you can actually see that there's current flowing. So you can detect that. You can even see the transient there. This is where we actually turned the fan a little bit faster, and this is where we turned it on, this is where we turned it off. So a lot of information that's just emanating out of the appliance directly without you having to interfere with it. So we thought, what else are the appliances emanating? And this is sound information that I'm going to spare you the details of the sound, partly because of technical reasons, but also because it's really boring. But just sound information from different appliances so you can see the difference. This is not just sound outside of the appliance, this is all actually sound recreated from the magnetic field or sound recreated from the current of the appliance. All of those give you different qualities of information that you can look at. So sound, okay? What about light? A lot of the devices that we have are modulated by light. And so we took this year one of our test beds to a lab that has a high-speed camera, and we wanted to record what it would look like to have a CFL, a compact fluorescent light bulb, turning on at a very, very fast frame rate. So these cameras are 27,000 frames per second. I'm showing it here at 1080x that. So this, every second that you're going to be seeing here is about 0.09 seconds of real world, and this is what it looks like. So just hold on. Pay close attention. So you can see the light bulb starting to warm up, and this is still the transient stage where it's not yet in steady state. And I think after here, what you're going to start seeing is the 120 hertz modulation that is just going up and down, brighter and then more dim, brighter and more dim, as the appliance is being regulated by the voltage supply. So this is imperceptible to the human eye when you see it, but if you record it really fast, you can definitely see it. And you don't need a high-speed camera to look at this. You could place a light intensity sensor next to it. And so we did that. We placed a very cheap photoresistor next to the appliance, and this is next to a CFL. This is the light intensity on the time domain, measured at 30 kilohertz, and this is the spectrogram of that corresponding signal. So even when the light bulb was turned off, this is off and this is on. This particular photoresistor is has less resistance when there is light. So even when the light bulb was off, we were recording ambient background radiation, background light intensity that had a lot of structure in the spectrum. And then when you turn on that CFL, all of that information is modulated by a CFL, and you can get to see a lot of interesting information. So for example, here in this 12 kilohertz region, we see a lot of interesting structure that we could probably use as additional information to do this aggregation. And again, this is a very simple photoresistor that you can buy off a Radio Shack and then just start collecting data from. We did the same experiment with an incandescent light bulb. You see similar patterns. We're still in the process of analyzing this data. This is fairly new. But I wanted to point out that this is information that we could easily capture. In fact, most of our computers already have light intensity sensors that we can leverage for that purpose. And it's probably a side channel that is worth investigating. So a lot of these devices can be thought of as Trojan horses in the house or in the buildings to collect side channel information from appliances. The next question is, okay, that's interesting, but how do you actually do it? And so that's why I think we need hybrid frameworks that allow you to incorporate that information. Okay? So here are some hybrid frameworks I've been working on with Henning Lan, who was visiting my lab this spring, someone who just graduated, and Kyle Anderson, who also just graduated from my lab. So first, let me tell you a little bit about what Suman was doing. So we think that there's an Achilles heel for the event-based approach, which is that because this is a pipeline that is just feed-forward, when you get to this stage, you're accumulating so many errors that you need to make up for all those errors. And this becomes a very complicated process to estimate energy in the presence of all the errors from event detection, classification, and so on and so forth. And so we came up with a framework for solving that energy estimation problem. It's not a probabilistic framework. It is pretty deterministic, but it solves the problem, and I'm not going to talk about the details of that here. What I wanted to show is how you apply the framework and what the framework is good for. If you want to read more about it, there's a link here, or not a link, but a reference to the paper where we documented the framework. So here's the experiment that we tried just to test the framework. So we bought off-the-shelf sensors, in this case magnetic field sensors that you can buy online, and we placed each one of them next to an appliance, and then we bought another commercial meter, a panel meter, in this case the energy detective, the TED, which probably many of you are familiar with. We connected it to the main meter. This was in our lab. So this panel has information about many different devices outside of the ones that we were measuring, but we wanted to use the framework to just estimate the energy consumption of each one of these individual devices by taking in information from the events that they were giving to us. Okay? So it does not require full deployment. You can basically just say, I have events from a particular appliance, and I know that those events are good. Can you tell me what that appliance, how much that appliance is consuming over time, just by knowing the full power and the events from that appliance? And this is pictures of the deployment, where we place the sensors, and so on and so forth. And here are some of the results. So this is the ground truth, the actual energy consumed over the time of the experiment, how many events we recorded for each one of the devices, and then this is the estimated energy. Actually, this is the ground truth. Sorry. So first of these columns, or the knee, is the estimated. The other one is the ground truth. And there's obviously some errors, and I can tell you that some of those errors are unavoidable. There are some of these devices actually have different transients that were hard to model, but some of them were avoidable. Like, for example, we have an air conditioner where we placed the magnetic field sensor close to where the fan is, but we didn't place it close to where the compressor is. And so both of them we couldn't capture. We only modeled one of them. And similarly, there's also a lot of problems with time synchronization. I'm sure that if any of you try this, any of these combination approaches will come into the same problem, which is you have a clock on one device and a clock on another device, and synchronizing the two to actually get a result is not that easy. Okay. All right. So I'm just throwing at you million-dollar ideas, and here's another one. Devices and hidden Markov models is a very classical way of thinking about eventless approaches. But what if you want to incorporate information from side channels? I worked with Henning Lang on this over the past few months, and we still haven't published this, but I'm just going to give you the broad brushes of the idea. What is the main concept? So we're going to model, instead of modeling each one of these hidden states as the state the appliance is in right now, we're going to model each one of the state transitions that happen. So let's say that you're in state 3 and you want to move to state 4. Which is on, and then the other one is off. We're only modeling exactly when those changes happen. And we're not modeling the presence of states as they go on. So essentially what we're doing is we're converting this HMM into an HMM that is only about events. So each one of these you can associate with an event, a statistically significant change in the main power consumption. And then we assume that the state emits all of the power signals between the event that happened there and the next event. So this state is responsible for emitting everything underneath there. But in addition to emitting the power signal, it is also emitting an additional feature that is related to this state transition. So this could be, for example, light intensity signal from the light whenever it turns on, or this could be sound, or any other feature that could or could not be related to power. So they could be statistically independent of each other, right? Or conditionally independent given S. And this framework you can obviously expand to more than one appliance and make a factorial model. And the complication obviously arises when you try to use this and to make inference. The best solution we've found so far is that we can think about the inference problem. Well, think about this model first as a discriminative model and not a generative model. So we're not trying to generate these signals. These are our observations, and we're just trying to make inference here. And we can use a modified version of the Viterbi algorithm to solve the inference problem. I say modified because if you try to use a full Viterbi algorithm, it's going to be very computationally complex. And this is what you come out with. The state conditional on the observations, so this is a super state. This is like all of these states combined. It's actually proportional to the prior distribution of the states, and then a product over all the appliances and all the events of these three models. One of them is a state transition model. The other one is an event emission model, which you can think of as sort of like the Bayesian inversion of a classifier. So this is like features given the states. And then a joint emission, which is where we're having most of the discussion about how to model this joint emission. So given a superstate, how do you model all of these different power traces? Do you need to incorporate the length of it? Do you not need to incorporate it? So on and so forth. So we're still working on this, but I think this is an interesting approach where you can start to incorporate information from side channels and then make the inference process more effective. Okay, so one more idea in the hybrid approaches before I move on to the next $1 million idea. So Kyle has been working on trying to move away from disaggregating appliances into disaggregating appliance ranges, or appliances that fall under a specific energy consumption range. So instead of having K be the number of appliances, what if you say the number of rooms, the number of activities, the number of people, the number of appliances that fall under this range, so on and so forth. And this is a more interesting model, maybe for some application perspective, but it's also a harder to validate model, because now we need ground truth about these things and not ground truth about the devices themselves. So I'm going to give you a few charts on the initial results that he's obtained on trying to do this with appliance bidding. So now we take, let's say, the blue data set, which many of you may be familiar with, and we try to take a histogram of all the events that happened, so all the delta P's that happened, the delta powers, and we do clustering, and let's say that we do clustering for 3 clusters, and we find that these are the 3 clusters that we looked at in that data set. One corresponds to 69 watts, 140 watts, and 1300 watts. And we discount the background cluster, which we take in from the beginning, because that's going to be present on any data set. And we then focus on trying to disaggregate these 3 over time. So the problem is that depending on how you set your delta P's, meaning how you detect the events, this histogram will change, and the clustering results will also change. So to make this unsupervised, what Kyle did is that he did a very broad search over all the parameters for the event detector, and then he organized them by the sensitivity of the detector. So how much error did it have from the actual ground truth energy for that bin, and then he found the settings that were more stable. In phase A of this data set, almost no change depending on the detector sensitivity. You can choose whatever detector you want. But in phase B, depending on how you choose the parameters for the detector, you may have very different clusters. So he chose the part that was more stable and then selected parameters according to that. And ooh, you don't have the last slide. So in the next slide of this, which isn't shown in this version, I have the results of this, and I was actually showing how the clusters evolve over time and what's the energy consumption of each one of these clusters. Unfortunately, that's not in this version of the slide, so you're going to have to trust me. It looks okay. There's a structure by day of the week. So there are some of the clusters, like for example, in phase B, this 25-watt cluster here doesn't show up on Saturday and Sunday. It only shows up on Monday, Tuesday, Wednesday. So there's some appliance in there, which we don't know yet what it is, but it consumes energy at around 25 watts that is not used on the weekends. So there's some interesting information that you can get out of it, even though you don't know what these appliances are. You're just saying something that consumes around 30 watts is turning on and off during these times, and that's it. Okay. Need to stretch? No? I do. Crowdsource high-resolution libraries. So why do I think this is interesting? Well, partly because of the Internet of Things, and we're going to start to get a lot more information from individual appliances as plug meters become more prevalent and you start to record that information. But also because to solve the original NILM problem, a lot of the work has gone into trying to identify what are the right features for us to extract from the data sets. And so we need some kind of library that has the required information for us to really tell what are the right features. Because right now we're doing feature extraction on small data sets, and everybody comes up with their own feature, and there's no consensus on how extensible or generalizable those features are. So with Jinkun Gao, one of my PhD students who's still in my lab, I'm working on trying to create such a database. So last year we published on BuildSys PLAID, which is a public data set for high-resolution electrical appliance measurement for load identification research. We just wanted to name it PLAID, so we found the right words to fit this acronym. That's really how it came about. So thousands of appliance records. We have a setup that we took around Pittsburgh. We went to people's homes. We connected appliances to this setup and collected 30 kilohertz voltage and current measurements for a couple of devices in the home, 1 second long. Actually, that's the published data set. The raw data set is about 5 seconds long for every appliance. So we just turn it on, turn it off, and that's it. And we did that for many appliances. 11 appliance types are in the data set and more than 100 makes and models. All of that data is available at plaidblog.com. And here's what it looks like in terms of the distribution, number of appliances, types of appliances. Here's a single datum from the data set. So we give you the instantaneous voltage, the instantaneous current, and this is, for example, a refrigerator turning on. So you can see the transient, you can see the steady state, and then we also give you the instantaneous power, which is just a multiplication of those two. Okay? So again, this is the distribution for each of the 11 appliance types. We didn't represent all of them evenly because that's naturally how they appear in homes around the area. And then this is around, across all homes, how many instances did we record in each one of the homes. So some homes we didn't sample too many, like maybe 3 devices, and some homes we sample a lot more. Okay, so what can you do with this data set? Well, the first question is, can we use this data set to figure out if the features that people have been proposing work or don't work? Here's the PQ plane, which many of you are familiar with. This is power and reactive power. For all of those appliances, well, actually for 3 of each one of the appliance types, 3 random data points from the data set. So you can see that even if you look at ACs, they vary a lot. So they don't cluster here very well in the PQ plane. So we tried different ideas. So let's say that we, instead of just using P and Q, we use Harmonics, which is something that was popular in the literature as well. Because Harmonics will not allow us to plot them in 2D or 3D, because we're using 7 or 8 harmonics, we needed to do some embedding. So we used the TSNE embedding, which you may be familiar with. This is T-distributed stochastic neighborhood embedding, which is very popular for visualizing high-dimensional data. And so here's a TSNE embedding for harmonics on the same data set. This is what PCA gives you, and this is the TSNE embedding. So not a lot of clustering in this embedding either. So this is just visual. Obviously, we can't prove anything conclusively, but it looks like harmonics themselves are not very informative for discriminating across appliances. This is current, just current, but voltage aligned, so it has information about the phase offset. And again, not a lot of structure. Maybe this appliance here, the microwaves, you can tell apart if you just do PCA or if you do TSNE. So we tried a couple of different features, and the one that actually resulted in the best results was this VI trajectory. If you read the NILM literature, there's a couple of papers called Appliance Signature Analysis, Part 1 and Part 2, where they started introducing this. And the idea is that you're going to plot over one cycle the voltage and the current in the same plot. And because this is very high dimensional, what we did is we gridded this and we binned it and then binarized it. So we have now a 16 by 16 image, let's say, that has 1 or 0 depending on whether the voltage and current meet at that point or not. And this is what the appliances look like. This is for the compact fluorescent light bulb, the hairdryer, and this is for the laptop. So if you try this as a feature and then you do the same embedding that we tried before, a lot more structure shows up. So now things are starting to cluster around the same areas, and you see cluster are very well defined here. So again, this is just visual, nothing conclusive, but it does show that maybe some feature like this one would be appropriate for discriminating between appliances. We tried a couple of classifiers using that binary image, and here's the best performance we got. As you can see, you wanted all of these to be high, but there's one that is really off. This heater is always confused with the hairdryer, which is not very surprising. So heaters and hairdryers are pretty much the same kind of component. So that hints at the possibility that these two may be impossible to separate given that information. So we may need additional information to solve that. Okay? And so this leads me to my final $1 million idea, and I'm not going to talk a lot about it. I'm just going to give it a 1-minute pitch from right here without giving any more slides. So a lot of the computer vision community and a lot of the other fields that are trying to do pattern recognition have gone from engineered features, or let's say human-tuned features, to unsupervised features. Or maybe features that are trained in a supervised fashion, but you don't select the parameters for those features by hand. And I think that the new wave of research in this area, once data becomes more prevalent and we have more access to data, is going to be on trying to do unsupervised feature engineering. My lab is starting to do work on that, but I guess you're going to see a lot more from other labs as well. In fact, I know people in this room who are working on that. All right, so hope does not come for free. That's the hopeful slides. Those were the hopeful slides. Now let's go with the challenges. And I don't know that I have a good handle on all the challenges, so I'm just going to give a few ideas of what I think are challenges. These are the obvious ones, right? Data, everybody complains about data. There's very little data. The quality of the data that's out there is dubious. And because there's very little data, we don't have enough representativeness for what we're trying to say. So a lot of the experiments we conduct are only conclusive within a data set, and most of the time they're overfit to the data set that we have. So I think we need a lot more data in order to solve or even answer whether or not this is possible. Another challenge that we're going to have to start to tackle head-on, and a lot of people in this room are trying to tackle head-on, is that when you're trying to do this for real, meaning with all the data that is available in some companies and with the models that are appropriate, the computational complexity increases. And there's a lot of computer science tricks that will need to be applied in order to reduce the computational complexity, or at least get approximate inferences out of the models we have. There's also time synchronization issues if you want to do this Internet of Things side channel information assistance. This is more of a technical solution, not really a research challenge, but I think one that pervades the type of applications that I've been working on, and I would like to mention it just so you can avoid it or try to be cognizant of it as you go on this field. So those were like the known things. Are there real challenges, you ask? Well, personally, I think that it may not be solvable. Like NILM, as originally conceived, may not be solvable. So it really depends, the solvability really depends on what you're defining NILM to be. And there are a number of niche opportunities in which NILM can work. And that's what we're seeing across all the field. Many of the startups that are coming out start with the general idea of doing non-intrusive load monitoring, and then in order to commercialize a product, they need to hone down into one specific application where they can actually prove some results. So depending on how you define the problem, it may be solvable, but I think that the general proposition of solving NILM just in the original way it may not be solvable. So where does this lead us to? So we've had 30+ years of research, and we have yet to see a silver bullet. A lot of different questions still abound, maybe the same questions that George Hart asked 30 years ago. The application-specific solutions will fare better and will continue to pop up. There's going to be more applications of NILM for specific cases. And just to remind you, and because this was the theme from the beginning, NILM is just a bridging technology. What we're doing today with NILM is to get the disaggregated results. Once the disaggregated results are obtainable through other means, NILM is going to be dephased, and so we're going to move on to something else. I don't know if that's a high note to end in. It's kind of a low note to end in. But this is really something we should consider, right? As a community, are we thinking about more the exciting technology behind NILM, or are we really interested in the results of NILM? If we're interested in the results, then we should start bringing into this community things that do not require disaggregation itself. We're using NILM as a tool. Having a workshop just on a tool year after year, unless the tool is still prevalent, doesn't make a lot of sense. So it's only a matter of time before this happens. there's probably going to be a few appliances that are not going to be available through these APIs, but it's only a matter of time before that happens. And so we have to start thinking about how to get there. Some acknowledgments from funding agencies, and then open for questions. I think I have 20 minutes.